Hello class, welcome to today's lesson, which is 2.2, and it's about conjugated binomials and difference of squares. And let's go straight to the exercises. I already uploaded the workbook 2.2 that consists of 20 exercises, and I believe it's very simple, but anyways, I'm gonna give you some examples in case you have doubts. Um, Most importantly for the difficult ones, because I know that you can handle the easy ones, but there are a couple of them that may be tricky. So I'm going to explain to you three examples. But let's first talk about what we need to do in this lesson 2.2. The main idea now is the following. If you remember, we already multiplied things like this. This is a binomial. This is its conjugated binomial, right? And we know right away without really developing the product, like in the extended version, we know that this will be immediately equal to the square of the first number, which is 4x. By the way, I'm sorry, I forgot the square here. There is a square. um, it's going to be equal to the square of the first number, so that's going to be 4x squared minus the square of your second number or your second term, which is going to be 9y to the fourth. And this is our answer, right? Which is known as a difference of squares because this number and this number are both squares. Perfect. We have done that, and that's very easy. Now, we're going to talk about the inverse problem today. For example, if I gave you now this difference of squares, if I said, guys, I'm giving you this difference of squares, please factorize it. Give me the product of conjugated binomials such that when you multiply this times this, you will get this. You see? So this is known as the inverse problem. The inverse problem is a factorization. Okay? And that's what the workbook 2.2 is about. It's about factorizing differences of squares. Ah, perfect. So that's what this is about. I'm going to give you three examples. So let's go straight ahead. I'm going to give you the example number 5 first. It looks like this: 9w to the 4 minus w to the 6. Okay, so we have in here, first of all, you have to make sure that this is a difference of squares, right? Because at first sight, you may not immediately notice that this is in fact a difference of squares. I mean, that it is a difference, that's sure, right? There's a minus in there, and that implies a difference. But how do I know whether this number and this number are squares? Well, I have to find out. That's the first thing we have to do. I'm gonna do it in blue. So first, I'm gonna ask myself, is this term the square of a number? And the same for this. Is this term the square of a number? So the way in which I do it is this. I'm gonna assume that they are. Okay, this is the square of this is the square of some number, and then we have minus, so I write minus, and this is the square of some number, and then I try to find out what number this should be such that when I raise it to the square I get this, and the same for here. What number should I place here, what term, such that when I raise it to the square I get w to the 6. Okay, so let's first look at the coefficient and take the square root of that. So it's going to be 3. Okay, why do you have to take the square root? Because that's going to give you the number, which is 3, right? Which, when you raise it to the square, will give you 9. You see, 3 to the square is 9. Now, what about the literal part? What about the variable? Okay, it's going to be w to the square. Okay, why? Because when I raise this w to the square, I'm gonna get w to the 4. Don't believe me? Do this. W to the square. And if you remember, by the laws of exponents, this is equal to w to the 2 times 2, which is equal to w to the 4, which is what we have in here. Okay? You have to learn the laws of exponents and have them memorized, preferably. Okay, the same with this other term. What number raised to the square would give me w to the 6? That's going to be w to the 3. Why? Because w to the 3 to the 2 is going to be equal to w to the 3 times 2, which is equal to w to the 6, which is what we have in here. So I already found my two numbers in here. And now I have, basically, if you notice, I have re-expressed this expression as a difference of squares, right? Because I'm talking about the square of this minus the square of this. So this is in fact a difference of squares. Okay? And now I can write my answer as the following. What's going to be the product of conjugated binomials? It's going to be this one minus this one, and then its conjugated binomial, which is this, right? This is our final answer. If you don't believe me, or if you don't believe yourself, or if you have a doubt at the end of any specific problem, now go backwards. Multiply this product of conjugated binomials, and you should be getting this, okay? And in fact, you will know. You will notice that this is the same as this. So this is the correct factorization of this difference of squares. Let's go to the next example. Number 10. 100 m to the 6 and to the 2 minus 81 m to the 2 and to the 4. This is a little more complex because now we have two variables in each of the terms, but it's not really that complex. Okay, what do I do first? I try to re-express this number and this number as the square of some terms. So I'm going to assume that all of this is the square of some number. Then minus, minus, and I'm going to assume that all of this is the square of some number. Now let's find these two numbers, okay? Okay, so what do we do? Take the square root of the coefficient. That's going to be 10 in this case, because 10 times 10 is equal to 100. And now, what about m? To what exponent should m be raised such that when I raise it to the square, I get m to the 6? That's going to be m to the 3, right? And to what exponent should I place n here such that when I raise it to the square, I get n squared, n to the 1. So I'm not going to write anything. And what about here? It's going to be 9 because 81, the square root of 81 is 9. And m and n to the second power. Okay? Make sure that the square of this number is this, and that the square of this number is all of this. Now, if you make sure, now we can go ahead. Now let's write the full answer. What's going to be the factorization in the end? Okay, it's going to be equal to the product, as we know, of two conjugated binomials. And what are going to be those binomials? They're going to be composed of these two terms. So let's write them down. 10m to the cube n minus 9m n to the square. You see? That's my first conjugated binomial. And the other will be 10m to the cube n plus 9m n to the square. And I'm done. This is my final answer. And again, if you want to make sure, you can multiply this, as we know, and you will get all of this. you should be getting all of that. Okay, so you see, it's really quite simple. But the basic trick is to re-express these two numbers as squares, as the square of something, the square of something, and then basically form with these new two terms, form my conjugated binomials. And the last example. Okay, these ones are difficult, so don't get stressed if you don't find the answer right away. I'm trying to challenge you a little bit more because you're gonna be IB students in the future, and you should be having challenges. Okay, that's the idea behind this program. Okay, now this is a little more complex, right? Because we have exponents that are not constants. I have 2n and 2m. So let's see. Like I've been telling you before, the fact that you have variables in your exercises and not constants should not change really the method in which you do things. So what do? I'm gonna presume or assume that all of this number is the square of something minus, and all of this number is the square of some other number. Okay, and let's find these two numbers. Okay, so to what exponent should I raise a? What exponent should be here such that when I raise all of this to the square, I'm gonna get a to the 2n. I'm gonna give you the answer right away, and you're gonna notice that it does make sense. The answer will be n. Okay, why? Because a to the n, all of that to the square will give me this, right? A to the n to the 2 is equal to a to that 2 times n, which is equal to a to the 2n. Why? Because we have the property, right? The theorem of exponents, which says that a to the m to the n is equal to a to the mn. That's why I can do this. And the same is going to work for b. The number that I should place in here is b to the m, because b to the m to the 2 will give me this. And that's it. I have found my two numbers. And now I just proceed to write my product of conjugated binomials, or the final answer. Okay, so one conjugated binomial, times the other conjugated binomial. And the conjugated binomials are formed with these two numbers, this number and this number. So let's go right ahead. An minus bm times its conjugated binomial. And I'm done. Again, if you want to make sure, you just have to multiply these two conjugated binomials like we know, and you will be getting that stuff. Okay, now if you have any question about whether this other answer is the same, for example, a to the n plus b to the m times a to the n minus b to the m, yes, of course, right? Because changing the order of products, placing this one at the beginning and this one at the end, doesn't change the product, right? It's like when I multiply 2 times 3, that's 6, or 3 times 2, that's also 6. The order of the factors does not change the product. So that's how this works, guys. I hope you have understood. If you have questions, please reach me on a message. And that's it. Complete all the 20 exercises for the next lesson. Thanks so much and have a great weekend.